I'm just going to go over this again real quick, some of this stuff. Just reminding you that a polynomial function is a function that basically has real coefficients and whole number powers. That's the easiest way to understand it. Real coefficients and non-negative integers means just whole numbers, whole number powers, okay? And the domain is all real numbers. So if you're looking at a function that has like a domain restriction, that is not a polynomial. Okay, so we already went over that yesterday. Okay, let's go on. Let's look at this next part. We said that this first one was a function, was a polynomial. The second one was not a polynomial, and that's because of the square root of x. First of all, x to the half, that's not a whole number power. And also, this thing is not hungry enough to eat any negative numbers. Can't plug a negative number into this function, so this is not a polynomial. Does anyone remember why we said part C here is a no? Yeah. It won't eat 2, right? So it can't be a polynomial. And the next one is actually a yes. It's kind of a trivial one, but it's a line. It's a horizontal line. Lines are in the polynomial family. And this last one, we FOILed it all out carefully, and we saw it was actually a negative x to the 5th, yada, yada, and it was a polynomial for sure. Okay? And then there's a little question here. It says, how do you find the degree without multiplying it all out? Well, for that, you can just think of this as, there's a negative there, but this is like degree 2, and this part here is some kind of a degree 3. You know, it's x cubed times, it's x cubed plus a bunch of other junk. So you can just kind of multiply the biggest terms. So what's x squared times x cubed give you? X to the 5th. So this is going to give you like x to the 5th, yada, yada. So you can tell the degree is 5 just by kind of looking at the highest powers of everything. We have an x squared and an x cubed. That's x to the 5th. Okay, so the ones that were yes, we're supposed to put a degree. And so for the degree, this is a degree 4, this is a degree 0, and this is a degree 5 polynomial. Hopefully you already wrote all this down. Okay, and then we were just talking about what it means to be continuous and differentiable. Okay? So continuous and differentiable. Two very important words. And I need to say a little bit more about these things, okay? So first of all, continuous. Here's a graph of a continuous function, sine, okay? Okay, so you don't have to lift your pen for that one. Even the absolute value function is continuous because you don't really have to lift your pen to draw it. But I wanted to show you a function that is continuous that you might have thought was broken, okay? So I don't think anyone in this classroom knows this, so pay close attention. You guys recognize this graph? What is it? You made a note card for it. Yeah, this is 1 over x, the rational function, the reciprocal function. You'll notice that this is actually broken, right? It is broken. But where is it broken? Like, where would you have to lift your pen when graphing this?
The axis.
Okay. Yeah, so you're supposed to give me an x value. Where is the graph? Where am I going to have to lift my pencil? When I reach x equals what? 0, correct. So, what's that? Yeah, that's right. This is actually considered continuous because although it's broken, the spot where it's broken was not in the domain, if that makes sense. So when you're graphing this, right, you do have to lift your pencil once, and that happens at x equals 0, but that point wasn't in the domain. So you were supposed to be graphing there anyway. You're only supposed to graph the domain part. And as far as the domain part is concerned, both of those pieces can be drawn without lifting your pen. So this is considered in the continuous family, and so is a graph like tangent even. Tangent, it's got all sorts of brokenness to it, there's that branch, and then there's this branch, and then there's this branch. And there's a break at 90, and there's a break at 270. But those breaks happen at spots that are out of domain. They're already at forbidden values. So we're not lifting our pencil there because we have to. We're lifting our pencil there because it wasn't even part of the domain. But as for the little branches themselves, they are perfectly continuous. So this too is continuous, as is secant and cosecant, and all those graphs with multiple asymptotes, they're all considered continuous functions. Okay, so this leaves us with a question. Can you think of a graph that is broken, that is actually discontinuous? There's one graph we drew this year where it's broken at values in the domain. Yes. Okay, so this is, for this year, right now, guys, the only graph that we have that is discontinuous, the only graph that is not continuous, is the step function. This is the only one we've drawn this year. Except maybe some piecewise functions. Remember this graph? This one is not continuous. Let me explain why. Because every time I have to lift my pencil, it happens at an integer value. So at x equals 1, you got to lift your pencil and switch up to the next rung. At x equals 2, you got to switch your pencil up to here. And those values, x equals 1 and x equals 2, those are actually in the domain. See the blackened points, the darkened points? That means those values were in the domain. It's not like there's an asymptote there. So you're supposed to graph at x equals 1, but you have to lift your pencil there. So this is considered non-continuous. All of these other ones are considered continuous functions, even though they have breaks. Those breaks happen at exclusions. Very subtle and interesting point. So it's very easy to think that if it looks broken, it's automatically not continuous. You need to know the domain first. Okay? All right, so there we said that. That's important. Now let's go and look at the word differentiable one more time. Make sure we know what that means. What does differentiable mean? So differentiable literally means without corners or cusps. And there's a few other things you need to know about it for next year, but we won't learn them this year. This is called a corner. For example, the absolute value function has a corner. And then this is called a cusp, like that. This is the graph of y equals absolute value x. That has a corner in it, even though it's continuous. You know, you can draw it without lifting your pen, but it has a sharp turn. And then this is actually the graph of y equals the cubed root of x squared. Looks like a seagull. Is that the right graph? Yeah, this is the graph of cube root of x squared. Or you could think of it as x to the 2/3. And honestly, that thing has a sharp, very sharp turn at the origin. See that sharp turn? Okay, so these are not differentiable. Not differentiable. The reason I'm bringing this up right now is because they are very important graphs, and non-differentiability is a huge part of calculus. But I want to tell you that polynomial graphs do not have corners and cusps. Polynomial graphs are nice and smooth, even x to the 99th, you know. If you look at x to the 99th on your calculator, you can try it if you want right now. If you graph y equals x to the 99th, it looks like this. Looks like this. It looks like these are sharp turns, but they're not sharp turns. If you zoom in enough, you'll see everything's nice and round. Okay? Okay, so that's actually what I want to do right now. I'm going to actually put up a graph on my WinPlot program. Okay, this is absolute value of x. Erase this old graph here. This is the absolute value of x. You recognize it. Graph the whole thing. See that? And if we zoom in on it, right, no matter how much you zoom in, it never looks rounded. I'm zooming in right now a lot. I don't want to crash my computer, so I gotta go slow. Just see that? It's a corner. I mean, that thing is a corner, is a corner, is a corner. There's nothing you can do about it. You can zoom in as much as you want. All of the points on this side a slope of negative 1 right here. Right? And everything on this side has a slope of positive 1. There's no exceptions. The only point that really doesn't have a slope is this guy. What's his slope? I don't know. Is it 1? Is it negative 1? No, it's not really either of those. So this is a point called a corner. It has a real sharp change in slope. Okay? All right? Now I'm going to type in a different function, but I'm not going to show you what it is. Give me 1 second. Here we go. What function do you think that is? What do you think?
X to the 100.
Looks like the absolute value function again? Sure does, right? Let me zoom in on it. This is how you can tell if it's actually the absolute value function. A little different, isn't it? Now you can see that the slope here might be like negative 1/2. The slope here might be like negative 1/4. The slope here is probably exactly 0, right? Like if you're drawing like little tangent lines. Okay, then over here, this might be like slope 1/4. You know, like rise 1, run 4, whatever. And this might be like slope 1/2. Very different from that last graph, even though they look kind of the same from a distance. Okay, so zooming in, we can see this one is definitely differentiable, even at the point that appeared to be a corner. But on that absolute value graph, it doesn't matter how far you zoom in. That thing is truly a sharp turn. Okay? And I suspect that Ghostwriter at Mossberry Farm has certain spots in the track where there is actually a kink in the track. So the tracks fit together, it's all continuous, but there are definitely changes in slope that are instantaneous. Because I know I get a headache every time I ride that thing. And it's not because of accelerations. It's because of the jerks. We call those jerks in the graph. Okay? In the slope of the track. There's something wrong with that ride. Does anyone else experience headaches there?
Yes.
I get them every time I ride that silly ride. I do not get that at Magic Mountain on any of their rides. Everything is smooth and differentiable. It would feel. All right? Okay, so hopefully that roller coaster analogy helps you kind of understand what non-differentiable points are like. Let's go on here now. We can talk about something, I don't think it's really new for you, but we haven't talked about it in a year, so scroll down to here now. If f is a polynomial function and r is a real number such that f of r equals 0, then r is called a real root or 0. And then there's two little subfacts here. R is an x-intercept of the graph of f. X minus r is a factor of f. This is very easy to understand, okay? So let me just spell it out for you with an example. Let's say that your function is x squared minus 2x minus 8. Can you think of a number that makes this come out to be 0? Like when you plug it in, you get an answer 0. Can you think of any number? 2 does not actually work. If you plug in 2, you actually get 4 minus 4 minus 8. 4 works. If you plug in 4, you get 4 squared minus 2 times 4 minus 8. It's 16 minus 8 minus 8. It really is 0. Okay, so what you just discovered is that since f of 4 is 0, 4 is a root. You probably already knew that. You've probably heard that before, right? Or some people call it a 0, or some people call it a solution, or some people call it an x-intercept. They're all the same thing for our purposes. 0, x-intercept, root, solution, they all mean the same thing. Okay? But what you may not have thought of was this problem could also have been solved by factoring. In fact, one of the factors is x minus 4, isn't it? Right. So these statements are all sort of synonymous, right? When I say that f of 4 is 0, I mean 4 is a root, and I mean x minus 4 is a factor. See, they all kind of go hand in hand. They all mean the same thing. And what's the other factor? Like what, if you factor this, what's the other factor? Yeah, this is x minus 4 times x plus 2, right? Yeah. So negative 2 is a root, and x plus 2 is a factor, and f of negative 2 equals 0, and you can make similar statements about negative 2 that you made to 4. So let's move on, though. Let's talk about how would you construct a polynomial if you were given the roots. Okay, so you've actually done this before, too, in your Algebra 2 book. Okay, so if negative 2 is a root, then x plus 2 is a factor. And if 0 is a root, then x minus 0 is a factor. And if 4 is a root, then x minus 4 is a factor. These are your factors. See? You can tell from the roots. Now, a polynomial that would have these factors would, in factored form, look like this. This would be the answer. This is a polynomial with the roots 0, negative 2, and 4. See? Now there's some questions I have, like, couldn't there be like 1,000 right here? I mean, there's no reason why I couldn't just put 1,000 right there. It just said find a polynomial with these 3 roots. I don't think it matters what that red number is in front. The roots are still 0, negative 2, and 4. So you could actually put any value here. In fact, I think I'll put 14. That's my favorite number. So I'm going to put 14 right there. You can put whatever number you wish. Okay? Or negative 14 if you like. Doesn't matter. It won't change the roots. Okay? Any questions on that? Pretty simple, right? Okay. Let's go on and talk about the next thing here. This is also something you've talked about before. If the factor x minus r occurs more than once, then we might call it like a double root or a triple root. Maybe you've heard those phrases. In this class, we're going to call them multiple roots. And however many times it appears, we'll call that the multiplicity. Okay? Multiplicity. Okay, for example, let's say you're doing a problem like this one, and you wrote down what this really means. This really means 2 times x plus 2 times x minus 1 times x minus 1 times 2x minus 1 times 2x minus 1 times 2x minus 1 times 2x minus 1. That's what it means, right? When you have a power 2 and a power 4, you're supposed to multiply everything out. This is kind of what it all means, right? And you can see that the x minus 1 shows up twice. And the 2x minus 1 shows up 4 times, see? So this is how you would describe it. You would say the roots are, and then you would just basically write negative 2, 1, 1/2. Those are the 3 roots for this problem. And the multiplicities are you can make like a table like this. The multiplicities are, let's see, how many times did negative 2 show up as a root? Only once, right? How many times did 1 show up as a root? Twice. How many times did a half show up? 4 times. These are the multiplicities. That's not very hard. It's not hard to understand. It's not hard to do. Do you really need to write out this long blue polynomial to see that? Not really. You can just look back at the original problem and just look at the powers that be. So this had a 1 power, this has a 2 power, this has a 4 power. Here's your multiplicities right here. They are the exponents on the parentheses of each factor. Okay, now last year, your teacher would say, 1 is a double root. And maybe you had a problem where there's even 4 multiplicities, and maybe Mr. Chen or whoever said, 1/2 is a quadruple root. I don't know if you ever ran into that situation. Well, what do you say when you get past 5, 5 is probably quintuple. What's after that? Sextuple, heptuple, I don't know, septuple. It gets confusing. So we're going to stop using that phrase. We're not going to say we're not going to say double root anymore. We'll say multiplicity 2. Okay? Just think of it as double root. Okay. Okay, new vocab word there. All right, let's go down and look at this here. What does it mean to have higher multiplicity? Like, does that even have meaning, you know? That's a good question. It has a very important meaning. I'd like to show you what it means today. Okay, so if you are running into a problem where, let's say, the root has multiplicity 2 or 4 or 6 or 8 or something like that, then that means that the function, the sign of the function does not change on either side of R. We'll talk about what that means graphically in a moment. And the graph touches the x-axis at R. Touches. Does not cross through, just touches. Does not cross the axis, it touches the axis. We'll talk about that. On the other hand, if R is a real root of odd multiplicity, you can probably guess what the blanks are here. This was does not change. This was touches, does not cross. If it's an odd multiplicity, the sign of f changes and the graph crosses the x-axis at R. Okay, this, I don't think anyone here has learned this, but it is a really valuable skill. Let me show you how I can use this to graph something. Okay, so can I erase this? All right, so let's go down here and look at this example. Okay, first thing we're going to do is find the x-intercept and the y-intercept. Now, there's going to be more than one x-intercept. Basically, whatever the roots are, those are your x-intercepts. Okay, so the x-intercepts are the roots. So let's make another one of those little roots and multiplicity tables. What numbers make this polynomial come out to 0? It's already factored. 0, 2, 0, 2, and negative 1, right? What are the powers on the parentheses? So 0 is coming from the fact that we have an x out front. What's the power on that thing? 3 powers, right? So 0 is a multiplicity 3 root. Okay. And then the 2 shows up how many times? Only 1 power that, right? So this multiplicity 1. Negative 1 shows up as a double root here, so you put multiplicity 2. Okay, watch closely. This is an odd number, last I checked. This is an odd number, last I checked. And this is an even number, pretty sure. Everyone agree that 2 is an even number? I hope you agree with that. Okay, this means that the graph will cross x-axis at 0, cross the x-axis at 2, but only touch the x-axis at x equals negative 1. Okay, so let's go back and answer the question. They asked us, what are the x-intercepts? They are x equals 0, x equals 2, x equals negative 1. We'll get the y-intercept later. Let's go to part B. We can write the graph of f crosses the x-axis at x equals 0 and x equals 2, but touches the x-axis at x equals negative 1. Okay, I think I can draw this function. Okay, watch how easy it is to draw this thing. Draw an xy axis. Okay. And put the x-intercepts on there. Okay, so we said that the x-intercepts are 0, 2, and negative 1. So that means we're going to have a point here, maybe out here at x equals 2, and then over here at negative 1 So these are my x-intercepts. Everyone agree? We've already determined that when the graph hits x equals 0, it's going to be a crossing point. Okay? So maybe it's going to go like this, right through the axis. Okay? When you hit x equals 2, it's going to cross the x-axis again, like that. But when it's at -1, it will not cross the axis. It will just merely touch the axis. So it's just going to kind of brush the axis like this. It's not going to cross through. It's going to touch it and stay underneath there. So this is a touch point. Right there you can see. And then I'm going to try to connect this graph. These are the only crossing points I'm allowed to have. Okay, now here's the graph I came up with. Does it look right? Well, there's one possibility for this graph, that it looks like this. But if you look closely at the original problem, we have an x here, we have an x here, and we have 2 powers of x here. So this is kind of like having x cubed times x squared, isn't it? Altogether, we have how many degrees? I don't really want to FOIL the whole thing out, but I'm kind of curious, what's the highest power of x if I did FOIL it out? What is it? X to the 6th. Everybody put your arms up like this. X squared, x to the 4th, x to the 6th should look like this, not like this, right? So this is the graph if the front was a negative. If there had been a negative out in the very, very front, this would be the right graph. But what happened here is, when I interpreted it crossing the axis, I should have assumed it crossed from above to below here, crossed from below to above here, and touched from above here. So the correct graph is actually the blue one, like that, not the red one. So I kind of used my knowledge of x to the 6th to figure out that it would actually be going up like that. There's some questions I still have, like I don't know where the highest point is right here. I don't know where this point is. Like I have no way of finding that without calculus. And this minimum down here, we don't really know where that is, but we got the rough shape there in blue. So you have 8 of these tonight. Okay, 8 of these to try on a worksheet.
Are you going to put it on Edmodo?
I already did.
Oh, okay.
It's on Edmodo. Okay, another thing you can do with this graph is you can draw what's called a sign chart. So this is not a full graph, but if you just list the roots, x equals 1, x equals 0, x equals 2, and x equals -1, and knowing that this resembles x to the 6th, you would know that it basically goes upwards like that. We know that x to the square, x to the 2nd, x to the 4th, x to the 6th all have that basic look of an even function opening upwards. Okay, so what you would do then is assume that this is positive out here. That means above the axis. And then, since -1 was an even multiplicity, you would assume that the graph hits at x equals -1. It hits the x-axis, but it stays above the axis. And then at x equals 0, that was an odd multiplicity, so it's going to hit the axis and actually switch signs. And when you hit x equals 2 again, it's going to hit the axis and pass through it, going from negative to positive. So this is actually called a sign chart. And if you convert it to an actual graph of the function, it looks like this. Plus means above the axis. Minus means below the axis. So this is what the graph would look like as we drew earlier. And we still don't really know where this point is and this point is, but that's a calculus thing we'll get to next year.